Okay, let's start today's class. Firstly, I'm sorry for late upload. Nowadays, I'm very busy, so sometimes my class will be uploaded a little bit late. Sorry for that. Last week, we learned about rigid body motion, and basic concept was homogeneous transformation and orientation using rotation matrix. Especially we learned about SO3, large SO3 and small SO3. And also we learned about small SE3 and large SE3. So let's briefly review last week. Firstly, large SO3 was rotation matrix. So this was a 3x3 matrix form. And this can be converted to small SO3 like this. So when it came from here to there, we use logarithm, and in the case of this way, we use exponential. So this one also 3x3 matrix, but this bracket means skew symmetric matrix, and this vector originally some kind of 3x1 vector. And this one is converted to the skew symmetric matrix by using this bracket, and that becomes small SO3. So this concept describes the orientation. Basically, this information and this information and this information having same information about orientation. So when you describe some kind of orientation, you can use this one and also this one and also this one, because these three expression is having same information but the different form. So because the reason why we having this kind of three form is when we calculate some kind of other kinematics or dynamics, sometimes we need this form, sometimes we need this form, or sometimes we need this form. So we should convert between these forms. And the other concept we learned was SE3. So this one is large SE3. In this category, there is a homogeneous transformation matrix. And also this one can be converted SE3, small SE3. Actually, this one we did not learn yet. Today we will learn about this one. What is this one? Similar to the SO3, in the case of SE3, there is a large SE3, and also there is a small SE3. So there are similarity in these two concepts. So in here, there is also log and exponential. So this one is very similar. So That is the one we learned last week. Until now, we learned about some kind of explanation or sometimes some kind of method to describe orientation and transformation. The reason why we learning about this one is the reason why we learn. Have you thought about this? Actually, in the undergraduate case, we only learned about this one and this one. If you learned about robotics class, you already familiar about this and this. But about these kind of things, yeah, this one is a little bit new concept. So the reason why we learn about this is we want to describe position and orientation together. Yeah, that is our goal. Actually, in the homogeneous transformation, there is rotation matrix and position matrix like this. So that was 4x4 matrix. So in this 4x4 matrix, we described about the rotation and the translation together. But more in the global concept, we want to describe position and orientation of rigid body and using this concept we can derive some kind of expression method to describe kinematics and dynamics more simply. So if you already learned about the dynamics, the dynamic equation is very complex, sometimes very the symbolic dynamic equation is very, very long and very, very complex. But if we describe this dynamic equation very simply, that is good. So the reason we learn about this kind of expression is we want to describe kinematics and dynamics more simply. So that is our goal. So if you're using the concept learned in this class. So if you use the concept learned in this class, you can write down the dynamics equation very, very simply, some kind of one line equation. So there is the power of this class. So in that process, firstly, we should learn about this concept. This one is one of the key idea to enable this kind of simple expression. For describing simply to describe dynamics equation more simply, we should learn about this concept. So let's introduce the concept of this one. This one is the twist. Yeah, we want to learn about twist. You may learn about twist, but some students is not familiar about this one. If I simply saying about the twist is some kind of expression type to describe the linear and rotation, linear and rotating motion together. So in here we want describe position and orientation together. So to enable this kind of concept, we have to have some kind of physical type to describe linear motion and rotating motion together. That is twist. Yeah, twist means when we twist something. Yeah, this one is twist. Yeah, some kind of drill. If you have a drill go forward when we rotate, and drill go backward when we reverse rotate. So that is the one of the type of twist motion. So in twist motion, there is rotating motion and linear motion. So we call it this kind of concept as twist. Okay, let's learn about twist. Here is a fixed frame S, and here is moving frame B, and there is rotation matrix R, and there is position vector P. By using R and P, we can write down the homogeneous transformation TSB as like this. So let's simply write down TSB as T. So when we write down T, it means this one. So if we take the inverse of T matrix, we can simply calculate the inverse of the T using the transpose of rotation matrix and transformation of rotation matrix multiplying position vector and minus. So this one is T inverse. And let's think about the T derivative, the time derivative of T. How can you get this one? So in the last class, we learned about the angular velocity, the space angular velocity and body angular velocity. This one can be calculated by R rotation matrix and R dot. Actually, R transpose and R dot. So when we R transpose R dot, it means body angular velocity, and R dot RT equal space angular velocity. Actually, the more strictly saying, there is the skew symmetric of angular velocity. Yeah, because this bracket means skew symmetry. So let's calculate T dot T inverse and T inverse multiplying T dot. Because if R changes by T, it becomes this one becomes this one. So the reason we calculate this one is there is some similarity in these two concepts. So there was some kind of special meaning about this one and this one. Then what is the meaning of this one and this one in here? So because there is some kind of similarity, it may be there is some special meaning about this one and this one. So let's calculate this. So T inverse is here, and T dot means this one. And by multiplying this one, we get this matrix. And it was body angular velocity, skew symmetric matrix of body angular velocity. And this one was linear velocity. This one is linear velocity, P dot, but there is R transpose. It means let's see here. P dot is linear velocity of origin of B. So in this figure, this one is P vector. And if because the B frame is moving, there is the linear velocity of the origin of B frame. It means P dot. And P dot is expressed in the S frame, based on the S frame. So P dot means P dot is PS, some kind of like this. But if we want change the basis, because R is RSB, R transpose means RBS. So if we multiplying R transpose, it means RBS. Here we can get this kind of deletion, and it becomes some velocity, because P dot, it becomes P dot P. And we simply express this one as VP. So it means by multiplying R transpose, we change the reference frame of velocity from S to B. So changing reference frame from S to B. So this one means linear velocity of the origin of B expressed in B frame. So that is the meaning of VB. This one is VB. And this one is angular skew symmetric matrix of angular velocity. Skew symmetric matrix representation of angular velocity expressed in B frame. So this T inverse T means linear and angular velocity of B frame relative to B, currently aligned with moving frame B. Yes. This meaning is a little bit difficult to understand, but this one is some kind of instant velocity of B frame based expressed in B frame. So when we describe the velocity of B frame, the reference frame can be in here or in here. So now let's think about B frame moving like this. So in this time, in every time it moving like this, and we think about some velocity like this. So in this time, the velocity of B frame, the velocity vector is like this. And in this case, sometimes B frame velocity like this. So this one is velocity vector. So when we describe the velocity of B frame, we think based on S frame, some kind of fixed velocity, fixed reference, but we also take the reference of B frame by itself. So in every time we can calculate the velocity vector based on B frame itself. So this equation means this one. The linear and angular velocity of B frame relative to B frame itself. But B frame which is currently aligned with the moving frame B. So in the instant, some kind of instant moment, there is reference frame B, and we can calculate the linear and angular velocity of B. And after the time, we also take the B frame as a reference frame, and also we can calculate this one. So this matrix means this matrix implying this information, linear and angular velocity. So then let's think about this one. This one is 3 by 3 matrix, and this one is 3 by 1 matrix. That means this matrix becomes 4 by 4 matrix. So let's think about this. This may be like this, because omega B square is skew symmetric 0, 0, 0, some kind of omega 3, omega 2, omega 1, omega 3, omega 2, omega 1, minus, plus, minus, minus, plus, like this. And 0, 0, 0. And here is Bx, Vby, Vbz, 0. This kind of 4 by 4 matrix. So actually, the matrix itself is not is bulky, because the essential value is here. So by taking the essential 6 value in here, we can make 6 by 1 vector like this. So this one is angular velocity and linear velocity, and this becomes 6 by 1 vector. So this nu b, this one is nu equal nu b. So we define this nu B as body twist. So here we firstly introduce about twist, and in the concept of twist, it includes angular velocity and it including linear velocity. So that is the concept of twist. So first three vector including angular velocity and last three vector including linear velocity. So as I already told, we want to describe position and orientation together. So the derivative of position means some kind of linear velocity, and derivative of orientation means some kind of angular velocity. So by using this twist, we can describe the position and angle, the time derivative of position and orientation can be described. So this nu b is spatial velocity in B body frame. Some kind, because the basis is B frame, we call it body twist. So actually the Greek symbol, this one is nu, but I will read this one as twist, just twist. Twist B. I will just read twist B. So the given spatial velocity twist B define notation as like this. Okay, this bracket means skew symmetric bracket, but this bracket means the matrix bracket. So do not confuse about this one. Actually, in the textbook, this bracket symbol a little bit different, but when we write down in here, it is a little bit difficult to express these two different bracket. So just consume this one is skew symmetric and this one is just matrix bracket. So in here we can get the small SE3. Yeah. So here I introduced about small SE3. What is the small SE3? This matrix, this 4x4 matrix, this 4x4 matrix is small SE3. So more correct expression about this one is Lie algebra of Lie group large SE3. So special Euclidean group image Lie group SE3, but this small SE3 is Lie algebra. We call it Lie algebra of Lie group SE3. So small SE3 becomes 4x4 matrix, and so there was T, the large SE3, and there is a small SE3. This one becomes twist. And twist itself, it is 6x1 vector. So when we take some kind of bracket, it becomes 4x4 matrix. So this one is SE3, small SE3, and this one is the same as T inverse T dot. So when we write down this equation, actually this bracket and this bracket and this bracket is three bracket is all these three bracket is different. Actually, how about using color? This bracket means skew symmetric. This bracket means skew symmetric, and this bracket, the red bracket means omega b VB. This kind of 6x1 vector becomes this kind of, by using this red bracket, we can convert this kind of 6 vector to 4x4 vector. And also, this one was skew symmetric bracket. So let's using blue pencil. So this blue bracket means skew symmetric, and this red bracket means converting from 6x1 matrix to 4x4 matrix. And also this bracket. This bracket means just the matrix bracket, the general matrix bracket. So this bracket and this bracket is having different meaning. But in the following class, I will use the same bracket. I will just same bracket, but when you understanding about this bracket symbol, you can recognize these three bracket having some kind of having different meaning. So this one is skew symmetric bracket, and this one is from twist. Yes, in twist there is two kind of format. The twist having two kind of format. One is 6x1 format, and the other one is 4x4 format. So twist itself, it is 6x1. So this one is twist itself, and the twist bracket becomes 4x4 matrix, and this one we just call it small SE3. So this twist can be converted 6x1 matrix to 4x4 matrix using this bracket. It means it is a little bit similar to the omega b, omega, the angular velocity having omega, that is 3x1 vector, but when we using the bracket, skew symmetric bracket, it becomes 3x3 small SE3 matrix. So this concept and this concept is very similar. So in the angular velocity, the 3x1 vector can be converted 3x3 format, and the twist also 6x1 vector, but it can convert it to the 4x4 format. It means SC3. So you should familiar about this kind of concept. The reason why we using this kind of transformation is to calculate more efficiently. In the computer, the matrix expression is more familiar to calculate some kind of matrix calculation. So when we for more efficient and fast calculation of matrix, sometimes we convert this kind of vector form to matrix form. So we learned about the concept of twist and concept of small SC3. And let's having some break in here and to continue next time.